are also called vertices. These are unique optical device which is having some thickness varying azimuthally around the center of the plate, and these plates are designed only for one wavelength and one topological charge, and this plate is placed in the waist of host Gaussian beam to produce optical vortices having some charge Q. By controlling the path length of this plate.
So again, can you connect that to your topological charge? I have an incoming plate wave.
Actually,
I have a polarization which turns that into.
Yeah, actually, this plate is like entirely composed by some spiral phase. So due to that spiral phase, we are giving here plane wave, and we are getting here helical wave.
And how do I get different topological charges?
Yeah, that plate is designed like that actually, which is having some singularity and all. That phase itself is having singularity, and we can see that singularity by looking at time.
That is because of the change in diffractive phase. Different parts of the light beam will be traveling different distances because that.
I understand what the principle.
So when the refractive index is changing, phase acquired by the beam will change.
Yes.
Because the propagation length will be different.
Yeah. So
because of that, the tracing logic will be happening within the Gaussian.
Okay, but that creates. Okay.
So next thing is Q plate. It is a liquid crystal device which is having some azimuthal pattern. We can see here, and azimuthal coordinate with azimuthal coordinate at the center. So this Q plate leads to the conversion of spin angular momentum to orbital angular momentum within the same light. And the sign of the output OAM beam is completely depends on the input polarization. If input polarization is left circular polarization, then we get positive. Then we get OAM with positive sign. If our input polarization is right circular polarization, then we get OAM with negative sign. So coming to my work, I've used here to produce optical vortices computer generated holography. So here on spatial light modulator, we have deposited 4 hologram which can be generated by using computer. And this spatial light modulator is illuminated by helium neon laser to produce optical vortices embedded with host Gaussian beam, and we have used aperture to select the desired optical vortex beam, and using CCD camera we capture the images up to m equal to 0 to 10, and I have shown here m equal to 0 to 4, 7. As we increase the order, the dark core is also increases. So coming to the perfect optical vortices, actually while we are using these vortices in communication, in multiplexing, we are using multiple modes to couple it, and each mode is having different radius, and it is very difficult to fix the radius using this optical vortices due to that different radius. So to overcome that problem, we are using new vortices called perfect optical vortices. These are having order independent intensity distributions. Means whichever order we are increasing, the intensity distribution is constant. Means dark core of the beam is same. So this can be observed. This can be generated by using Fourier transform of Bessel Gauss beams, and this is the equation for POV beams. So these are the applications: free space communication, cryptography, optical imaging, and one more thing, optical research. So this is the experimental setup for generating optical vortices. Initially, we have generated optical vortices, and those optical vortices are passes through the axicon. Axicon will does the job of conversion of optical vortices into vessel gauge beams after certain distance. So we have we got here at this point we got vessel gauge beams, and as we know, the definition of POV beams is nothing but Fourier transform of vessel gauge beams. So to make the Fourier transform, we kept one lens. After the same focal length, we have captured the POV beams using CCD camera, and we captured here from 0 to 10, and I kept some images over here. As we see here, as the order is increasing, the dark core is constant. So this size and width can be changing using different axicon. So this is the plot for radius of bright ring versus order of the POV beam. So by looking at the plot, we can confirm that as we increase the order, the radius of the bright ring is constant. That means it can confirm that quality of POV beams. Formation of speckle pattern. So speckle pattern is nothing but random granular pattern, which can be obtained when coherent light passes through the rough surface. Rough surface is nothing but like it is having many inhomogeneities which are randomly distributed. So speckle pattern is nothing but speckle pattern, we can get interference of many scattered wave fronts which are induced from many inhomogeneities of the rough surface. So here we scattered our POV beams through ground glass plate which is having many inhomogeneities and recorded the speckle patterns. So this is the diverging speckles. So speckle size is nothing but spatial length up to which correlation exists. So here we did speckle size using some MATLAB coding by doing autocorrelation itself with same image. So in some near fields, the mutual coherence function is this one. So we did some mathematical calculations and all. Finally, we get the equation for speckle size. So as we can see here, the speckle size is directly proportional to the propagation distance, and it is independent of order. So from this equation, we can easily say that as we are increasing the propagation distance, the speckle size is also increases. So this is the experimental setup for generating the diverging speckles. We have generated the POV beams initially. Then we passed those POV beams through ground glass plate, and we capture the images for different propagation distances from Z equal to 20 to 70 in each 5 centimeter interval, and those images were captured by CCD camera. Okay, these are the speckle patterns for order m equal to 0 at different propagation distances 20, 45, 70. So from this figure, we can see as we increase the propagation distance, the speckle size is also increases. That means speckles are diverging in nature. So here, so from this plot, if we are increasing the propagation distance, the speckle size is also increases. That means speckles are diverging. So both theoretical and so this red dots are theoretical and the blue are experimental. So both are well matched each other. Then, as we said here, the speckle size is independent of order also. For a particular propagation distance, if you are increasing the order, the speckle size is constant. So here, for a particular propagation distance, speckle size is constant for all orders. Here, actually, order is there. Now, non-diverging speckles. So, in case of far field, the mutual coherence function is this one, gamma dash of delta r. So, speckle size, as we done some mathematical calculations and all, then the speckle size is 2.4 lambda f2 by 2 pi rho naught. So from this equation, we can easily predict that this speckle size is independent of propagation distance and order, independent of order also. It depends only on the focal length f2 of the Fourier lens. As the propagation distance increases, the speckle is constant. Speckle size is constant. That means these speckles are non-diverging in nature. So this is the experimental setup for generating non-diverging speckles. So initially for diverging speckles, we kept our camera here just after GGP, and we changed our propagation distance and we recorded the speckles. But here we are doing we kept one more lens to make the Fourier transform of near field speckles. So after the focal distance, we used some propagation distance, and we have imaged speckle size speckle images for different propagation distances in each 5 centimeter interval. So these are the speckle patterns for order m equal to 2 at different propagation distances 12, 27 and 42. So here we are increasing the propagation distance, but our speckle size is constant. That means speckles are non-diverging in nature. So from this figure, we can see as we increase the propagation distance, the speckle size is constant. These red dots are theory and these blue dots are experimental. So this theory and experimental are matched. So we have proposed one technique for generating the diffracting as well as non-diffracting speckles using scattering of POV beams, and we have also provided the exact analytical expressions for near field and far field speckles. And we have proven that in near field case, speckle size is directly proportional to the propagation distance, but whereas in case of far fields, speckle size is independent of propagation distance. In both cases, it is independent of order. Thank you.
Any questions? Any basic notes?
Yes.
No one else has questions. You already asked. So those speckles you are related to a certain characteristic of my material. You said that they are coming from impurities in my liquid crystal or whatever. So speckle size is related to a physical density or size within that object. Or how can I just very naively interpret this one pattern where they diverge, and in the other case they stay of the same size regard? So I would expect that if I take into account this, if I relate the pattern I observe on my screen to whatever property I have in my crystal, that the speckle size, this physical property, remains invariant if I did my calculation correctly.
Actually, that is in case of like if we are doing again Fourier transform of that speckles, whatever we got initially, then we get that non-diverging speckles. Means even we are changing the distance, the size is constant.
Yeah, so it shouldn't matter on what kind of light I shine on it. The speckle size is something, it's a property of my material. And this diverging phenomenon is something which I observe only, or how do I, what is, the speckles are not diverging. It's a property of my, it also is. Okay, I'm sorry, now I thought, okay, thank you, sorry.
Anyone else? Basic questions, anything?
So I have very general comments actually.
Okay.
So I think the motivation for this one actually to give a glance of your work to your colleagues is like whatever the presentation you made is good. And I have seen already in your extension meeting and other. Okay. So this presentation, what you made is basically for a specific audience who is working on your field. And here we have a very diverse audience. So it's for everybody. We have very diverse audience. So first you explain like why you doing it. Okay, and your why you did PhD and other things are first slide is not required for this presentation, right? So this you can everybody can remove. Okay. And you can give a little bit more like application of it. And a little bit about more example like what is hexagon, what is convex beams. And then you can start your presentation. Then you can connect your audience. So different monomers, if you are preparing, prepare like that, right? So that your friends can know like what you are doing, rather than that showing the graphs and your results, your publication. You just say like what subject you are doing. That will be more interesting. The presentation is good, but actually it's very specific to the audience who are working in this field.
Sir, I have a question. I don't know like whether this question is related to that field or not. But when light passes from lower density region to higher density region, it deviates from its path. Like why it deviates from its path? Like what happens molecularly so that the light deviates from its path? Like it moves towards the normal.
Yeah, it's velocity.
Yeah, I know. Velocity changes and its path changes, but why?
I know refracting is you know about refraction, yes,
No, but he was asking about the molecular.
Yeah, like what are the factors that is making the light bend? With the data given, like we can derive all the
light bending is due to the continuous variation of reflection. Continuous variation. It's not like from one medium to another medium. Let's say we take 1 centimeter. From this point to this point, we will be having a variation in the reflection. Then only light will be following the curve. Otherwise, it will be like straight line. So if the curve path means refractive index will be continuously changing the position.
But that was not the question. The question was how to explain this continuous variation based on a microscopic, molecular, atomic, quantum mechanical picture. That is the question.
That will be the specific case for the individual molecules, like individual materials, okay, where we are designing them. Okay, so that's like it's not the like broad question of what is happening. When we talk about particular materials, like kind of metamaterials, like when we take some examples of the materials, so that will be a problem. Like we need to discuss on specifically for this material what is happening. Okay, like we have some examples where according to general theory of relativity, light will be building, right? So that will be specific. What is happening in the molecular. So there are some materials where we are having the coupling between magnetic and optical properties as well. So there also maybe
so like they are influencing the light to change its path.
So the only parameter influencing the changing the light path is refractive.
Okay.
How refractive index is varies with according to the material properties, but is also affected. Okay, we need to have the coupling between these two in order to answer the question. Okay. But by changing the properties of light, propagation only refractive. But how it is related to your okay, this thing that depends on the material. Of course, it is more specific. Okay, for every material.
Any other questions? Okay, so we'll have a short tea break. After that, we'll come for Malleswari. Okay, just 5 minutes.
The presentation talk is a room temperature polar and weak ferromagnetic oxide with low dielectric loss. This is the outline of my presentation. So introduction to multiferroids, motivation, objectives, result and discussion, and conclusion. The material which exhibit more than one ferroid ordering, such as ferromagnetism and ferroelectricity, are known as multiferroids. It is difficult to achieve in a single phase as
ferroelectricity and ferromagnetism because there is opposing electron structure requirement. For example, ferroelectricity requires closed shell, whereas ferromagnetism requires open cell structure. This picture shows different routes to design multiferroids. We are interested in room temperature multiferroids. As we can see that we are exploring room temperature multiferroids with bismuth-based perovskites has lone pair ferroelectric and d-electron magnetism. One of the multiferroic is bismuth iron oxide. It has ferroelectric and antiferromagnetism at room temperature. However, it has bulk phase due to its no net magnetism because due to the spiral spin of this magnetic material, there is no magnetization and it has a linear magneto-electric coupling. Multiferroics are used in like sensors, actuators, and transducers in memory devices also. For example, here we can see FERAM means ferroelectric random access memory. This is a type 1 multiferroid. It has only, for example, in FERAMs, example is material is bismuth iron oxide. It has means fast processing and short storage memory it has. Whereas in MRAM means magneto random access memory. In this memory, this is a type 2 multiferroic. Example is bismuth manganese oxide. In this system, we are using large storage density. That material has large storage density and low processing. As we combining these two materials means a small amount of substitution in bismuth iron oxide, the material get drastically changes its properties. Means these are getting fast processing and high storage density. Known as MERAM means magneto-electric random access memory. If this magneto-electric random access memory shows non-volatile, high speed, and we can read and write also in these memories. In ferroelectric memories, it is only write-only memory. In MRAM, it is read-only memory. This MRAM is only for write. By combining this, we are getting read and write with high speed memory device we can develop. So, a substitution of small amount of magnetic ion increase magnetic properties means like reading and writing speed will be increased, but it changes its centrosymmetric. So this they make one new strategies to make room temperature multiferroids. In this system, first they took polar rhombohedral and polar orthorhombic materials to combine morphotropic phase boundary. In that morphotropic phase boundary, the compositions are ferroelectric. By increasing a small amount of magnetic ion is sustained both ferroelectric and antiferromagnetic. Magnetic properties also will increase by adding the small amount of magnetic ion. So it is in this strategy they made room temperature multiferroids. So we are interested in this process. So we explored. No, not good. So our aim is to design room temperature multiferroids with the morphotropic phase boundary. So we explore. We proposed bismuth 2x3 titanate as a tetragonal or orthorhombic. We don't know that phase, but we are proposing this is a phase, polar phase. Then we all also know bismuth iron oxide. It is ferroelectric and anti-magnetism at room temperature. So we took this and combining this two solid solution of bismuth iron oxide and bismuth titanate to make a morphotropic phase boundary. We are anticipating it that the morphotropic phase boundary we got. Maybe we are expecting we are getting room temperature multiferroic. So we explored a ternary phase diagram between bismuth titanate and bismuth iron oxide and calcium titanate. As we can see in ternary phase diagram, this line and this line, the solid solution between bismuth titanate and bismuth iron oxide. In this phase, the composition shows secondary phases. So further, we are studying this in this. We are studying the further region. This is the intermediate region. In this region, the composition shows perovskite plus secondary phases. For increasing the bismuth iron oxide and the calcium titanate, in this region, we are getting phase pure perovskite phase, as we can see in the XRD pattern. The phase pure composition, we study the structural analysis of that phase pure composition. We are getting the rhombohedral structure and R3C space group. We define the lattice parameters as we can see in the table. The change in lattice parameters conforms with a rhombohedral structure. Further, we study the structural analysis of this composition. We study by using the same analysis. The composition shows fine grains, and with the help of EDS data analysis, we reaches the target composition. Further, we study the electrical properties of the composition. As we can see from the graph, the dielectric constant versus frequency and loss. The composition shows very low dielectric loss. This loss is essential for measuring ferroelectric measurement. And we are studying the SHG measurement, second harmonic generation measurement. In this measurement, we are getting the composition is a polar. It's just an indication. Further, we study whether the composition shows phase transition or not. So we explored. We need temperature dependent measurement. So we made one custom made impedance probe and furnace. By using this setup, we measured the sample with a high by increasing, with varying the temperature. As we can see from the graph, the dielectric constant versus temperature, a high peak shows at 302 degrees centigrade. The high peak indicates it's a phase transition. In second panel, the heat flow versus transition, a small bending peak indicates it's a phase transition. Further, we are studying, whether the composition is conductive or not. So by using this, custom-made impedance probe setup, we measured the impedance study of this composition. As we can see at the low temperature, the composition shows single semicircle. That is single semicircle, and it's telling about the capacitance of the material is 10 to the power of minus 11 farad. Means it's a grade. Further, we are increasing the temperature, and we are seeing this two semicircle, but it is a small cam. Means here two contributions are there. First one is grain, and another one is we are identifying with the capacitance value 10 power minus 5, suggesting this is a contribution from electrode response. After that, we measured that Arrhenius by using Arrhenius plot. The activation energy of the grain boundary is 1.159 electron volt. The electrical and magnetical properties of this composition. As we can see, the PE loop of this composition, it shows non-linear ferroelectric. After that, we measured a magnetic measurement of the composition. The MH loop suggests at room temperature, it is a weak ferromagnetic or canted anti-magnetic behavior at room temperature. At by one more thing, we are looking for phase transition also. So we increasing high temperature, room temperature, high temperature magnetic measurement of this composition. So the phase transition appears at 557 kelvins. And one more thing, we studied the Newton diffraction of this composition. See, this is a normal XRD, and this is a Newton diffraction. In this XRD data, we are getting one additional peak. This additional peak indicates the long-range magnetic order. These are also Newton diffraction with a different wavelength. So conclusion, we explored a ternary phase diagram between bismuth iron oxide and bismuth titanate and calcium titanate. And we are getting a composition, phase pure composition. The composition shows a rhombohedral structure and R3C space group. And we are getting the composition as a low dielectric loss. For Newton diffraction study, it shows long range magnetic order. For SHG measurement and ferroelectric measurement, the composition shows polar nature. This is my publications. And I would like to thank my professor, my supervisor, Dr. Pranam Mandal sir, and the SRM University for support, encouragement. And I would like to thank my collaborators and DST for funding. Thank you so much.
So, if you talked about phase transition.
Yes, sir.
So, two phase transition you talked about.
Yes, sir.
One is magnetization. Right?
This one, sir.
This one is a dielectric constant, right? And another is magnetization.
Yes, sir.
Okay. So the magnetization is the next one. Yeah. So at that room temperature you have higher magnetization, and when you increase, then you get
Low magnetization. Yes, sir.
So what is the structure? You just can you say that what is the structure at? Means what is going on structurally?
Structurally, it is here in rhombohedral structure. While increasing the temperature, the rhombohedral is going to the cubic.
So in that
See here, here we are getting cubic structure.
and what about that other case?
Other case also same, sir. That is, this is for electrical study. That is for magnetic study. Just we are confirming whether phase transition will appear or not.
But here the phase transition occurs around like 300 degrees.
Sir, it is converted into Kelvin, then it will.
Oh, it is in
Next, yes, a degrees.
and that plot is that plot is in Kelvin.
That is in Kelvin.
So why did you plot?
Yes, I will.
You will use the same.
Yes, yes.
Some magnets can like erase the data from the hardware. So what exactly?
Yes. Hard means here in this drives, just we are making the materials only. We are not expertise and devices. Okay, means actually in ME RAMs it is a speed. It can read by using electrical motion. It can read. I mean, it can read and write also that memories. This means by using this ME RAM, so we can reduce the volatile because of high speed of electrons. Memory will be damaged. So in this, by using this process, we can reduce that volatile nature of the memory.
And 0, 1, the things that are stored in hard drive is in form of spins, right?
Spins only. One spin is up, that is 0, and spin is up, that is 1, and spin is down, that is a 0. you are calculating that RDS for activation. What is your rate constant for that? How you are calculating? No, just we are taking the just we are plotting that data, and after that we are fitting that this curve in origin. After that, so what are the parameters for calculating the activation energy? Activation energy, we need resistance versus area. That we are using one pallet. So we are giving that pallet area and that radius, means our resistance.
Malaysia, do you want to explain to them that instrument?
This one.
Yeah, how you do? What are the special things of Fruitsy? Are you keeping that for yours?
That is
The furnace. I think Fruitsy will keep it for this. Anything else? Yeah, so thank you for the speakers. If you still have any doubts, you can still continue discussion with them. You know now what they're working on. You can talk to them about it. You can clear your doubts with them. So I wanted to discuss about the next talks that we're going to have. As you know, it will be next month. So the professor will be able to join us. So we are thinking of next is supposed to be Ramya and Afzal. We are supposed to be in June, right? Ramya, is it? Yes. Yeah. Again, so we're supposed to be in June, but what we'll do is keep it in the first week of July. That is, I think the next closest Friday is 1st July. Okay. So tentatively we'll keep it 1st July. I'll extend the official mail once it's confirmed. And after that, almost in July itself, we'll have another talk by Bhaskar and Anjana. Okay, that will be on the last week, 29 July. They'll confirm the dates. Okay. So, anything else anyone wants to add? Wants to give suggestions apart from the snacks? Okay. So, yeah, so thank you all for coming, everyone, and thank you for interacting with us. We hope to see you all again on the next department research series. Thank you.